Hey guys, welcome to the LearnAP Chem live stream. So last live stream we talked about calc problems, but now we're gonna be going over chemistry. So if you guys have any questions on AP chemistry, sure to ask them in the chat. Otherwise I can get started on just some general things that might confuse you. Alright, so for the time being, I'm going to go over just some general trends across the periodic table. I talked about this in my last video. I'm sorry, not in the last video, in the third video about the periodic table. But I'm going to go over these just because they come up sort of a lot and you should definitely be familiar with them. Okay, I'm sorry, it was talked about in the second video. Hund's rule, orbital box. Okay, here we go. So, first trend we want to talk about is electron affinity. And again, this stuff comes up a lot, so you should definitely make sure you sort of understand this stuff. But as I talk about this, if you guys have any questions, be sure to leave a comment and ask. Okay, so as stated on screen, electron affinity is the amount of energy released when an electron is added to a neutral atom or molecule as a gas to form a negative ion. And I see we have our first comment. What's going on? So we're just talking right now about electron affinity and just trends across the periodic table. I mentioned that this stuff sort of comes up a lot and you should be familiar with it. But this was talked about in my second video. I'm just going to go over this stuff before we have any questions. But if you have any questions, be sure to ask away. So anyway, electron affinity is varying diagonally across the periodic table with fluorine. Okay, so this is the most confusing. So I'll make sure I spend some time about it. So, why don't you sort of just tell me what is confusing you about it? I'll go over it and then sort of try to explain it to you better. So what is confusing about electron affinity? It's basically, so the very concise definition is the amount of energy released when an electron is added to a neutral atom and forming a negative ion. So it's sort of similar to electronegativity, which is, you know, okay, no, it is not. The opposite of electronegativity would be the ionization energy, which is talking about removing electrons from an atom. Electronegativity is describing the attraction of electrons to an atom, and electron affinity is talking about the amount of energy released when an electron is added to a neutral atom. So they're not opposites in terms of definition, and they vary the same way. So with electron affinity, fluorine has the lowest, meaning that when you add an electron to fluorine, it's releasing the lowest amount of energy. However, the lowest amount of energy compared to all the other elements. However, so that's right here. However, francium, if you added an electron to it, would release much more energy. In fact, the most on the periodic table. So we have this sort of diagonal trend. So as you go down and to the left, we have higher electron affinity. So it's important to note that, okay, that makes sense, good. So it's important to note that this is a diagonal trend. So you know, what trips a lot of people up is they'll say, we'll have an example. Which has a higher electron affinity? We'll say lithium or carbon. So as I talked about, we have this sort of diagonal trend. As we go down this way, we're getting a greater and greater electron affinity. So for most people, if you know that, it's sort of obvious that we have lithium here, we have carbon here. Okay, so we're going this way. Obviously, lithium is the higher electron affinity because it is to the left of carbon, and that's the general trend. However, so that one normally, if you know that, doesn't really trip people up. However, let's say we had carbon or I believe that's tin, SN, yeah, or tin. Just had to make sure. I'm sorry. So here's tin, here's carbon. They're in the same group. So it's not immediately apparent what the answer to this question would be. But you have to remember that this is a diagonal trend. It's not right to left, it's diagonal. So in addition to as we're going left, we have higher electron affinities. As we go down, the same thing is true. So here, tin, although it's in the same group, it's in a higher period than carbon. And as we know, as we go down and to the left, we get higher electron affinities. So we can say that tin here has the higher electron affinity. Because again, the diagonal trend applies both from going right to left and going top to bottom. So just something to keep in mind. When I was first learning this, that sort of tripped me up. Okay, so good question here. Is the electron affinity for fluorine the lowest? Because when an electron is added to fluorine, it is isoelectric to a stable element. So Arnold brings up a good point. So if I have just, we'll say, the orbital diagram for fluorine, or I'm sorry, the Bohr model, our atomic number is 9. So I'll just quick draw this out. So 1, 2, 3, 4, 5, 6, 7, 8. We have a full outer shell here. And this is F minus. So he brings up a good point. So when we add an electron to fluorine and we get F minus, fluorine's octet is complete. It's a stable, its octet is full. So if you guys know anything about this, or you might have heard of it, it's called the Octet Rule. So meaning that every element wants a full outer shell of electrons. So here for fluorine, the easiest way for it to get a full outer shell is to simply add 1 electron and become F minus. So when you add sort of one electron, it does that. Now again, this plays into the natural dynamics of fluorine. These electrons are repelling each other, and unless you have sort of a positive element to attract to fluorine, it's not going to do this on its own. However, that's why it has the lowest electron affinity. You're absolutely right. Is that when you add an electron to fluorine, it's going to become its octet is going to be full. Its outer shell will be full. And thus, it's isoelectric to what you say stable element, just meaning that its electron configuration is the same. Now, it's worth noting why fluorine would have a lower electron affinity than, say, chlorine. For both of them, you add one electron, you get a full octet. So why aren't they the same? Well, chlorine, so I'll just simply draw this here. Fluorine, I have 2 energy levels. So this is n equals 2 as our outer shell. For chlorine, I have 3. So n equals 3. So when I add this electron, so electron affinity doesn't apply to noble gases. In general, noble gases have a very high electron affinity just because they have a full octet. So in terms of the general trend, you're absolutely right that this would not apply to electron gases, noble gases. You wouldn't really be asked, like, does neon have a higher electron affinity than, say, calcium? But you might be asked, does neon have a higher electron affinity than krypton? And the way you would answer that is simply what I'm going to talk about now, is that the reason that fluorine has a lower electron affinity than chlorine is that the electron you add is much closer to the nucleus. And so the same would go when comparing 2 noble gases. So to answer your question very succinctly, the general trend of electron affinity decreasing diagonally like so does not apply to noble gases in the sense that helium does not have the lowest electron affinity. That being said, as you move down, because we're adding electrons further and further from the nucleus, the trend absolutely applies. But you could not, so in other words, it works top-bottom, but in terms of right to left, just ignore the noble gases, I guess. So I hope that answers your question. If you have any more questions about, electron affinity, ask away. Otherwise, I can talk about, so the distance to the nucleus plays the primary role in the amount of energy released. I wouldn't say primary. It plays a role in terms of, like I said, if you're comparing 2 elements in the same group, it's going to be the only factor because both, have the same amount of valence electrons. However, okay, so I'll write this out just to make it a little more clear. Factors in electron affinity. So our first is the distance to the nucleus. And secondly is number of valence electrons. And when I say that, I'm really talking about how many more electrons do we need for the full shell. So shielding doesn't play a factor. Shielding absolutely plays a factor. Okay, I'll write that down as well. Shielding. Electron shielding. So yeah, I also forgot that shielding is also playing a factor in, as we go down, the electron affinity is going up. Because electrons are sort of shielded from the nucleus more, our electron affinity is going up. So what causes the amount of energy to increase? For that explanation, I think you would need, like, some sort of physics explanation for that, but just know that, just think about it as the atom wants the electron less and less as we go this way and as we go down. So, thinking about it, fluorine, while it doesn't really want an extra electron, it's going to take it because there's not a lot of shielding. We have 7 valence electrons, and our distance to the nucleus is going to be close, while francium doesn't really want the electron because that electron, there's a high distance to the nucleus. Let's see what the atomic number for francium is, 223. So we have a lot of shielding, so 223 for francium, 9 for fluorine. And then number of valence electrons, francium is 1, but it would much rather lose 1 electron than gain 7. So is this all the stuff that is going to be on the exam? They're not going to ask you this directly. They wouldn't ask you factors in electron affinity, but this is just something to sort of understand why the trend is there. But in general, can probably get away with just knowing this. But I would definitely just understand why that's the case, because things like distance to the nucleus, electron shielding, valence electrons come up all over the place. So if you understand why electron affinity works, you can understand other concepts much, much more easy. So again, if you have any more questions about electron affinity, anybody, just be sure to ask away. Otherwise, I can move on to some other stuff. Electronegativity, as I stated earlier, is very similar to electron affinity. The trend is the same, and then everything I said about factors in electron affinity also apply to electronegativity. However, they vary in definition. So electron affinity is basically asking, what is the amount of energy released when I add an electron, when it becomes an ion? How does an atom enter the excited state? Okay, so actually that is not how an atom enters the excited state. So let me just draw the Bohr model of hydrogen here. Very simple. So this is what we would call the ground state. And this means that all of our electrons are in our lowest possible energy levels. So here we have this first energy level, and this electron can't go any lower. If I drew hydrogen instead in the excited state, I'll draw this in red. That was a terrible circle, I apologize. Okay, here. Okay, there. So here would be an example of hydrogen in the excited state. Its electrons are not in the lowest possible energy level. This electron here is at n equals 2, but it could go to n equals 1. N equals 1 is unoccupied. So this is what we mean by ground state versus excited state. We're talking about, are our electrons in their lowest possible energy level? So how you would get to the excited state, to answer your question, would just be you're adding energy to the atom. So you could heat that up, you could heat the atom up, you could Okay, so what causes the electrons to jump levels? So this is the same question as how to get to the excited state. So you're adding energy, so that could be you're heating it up. You could bombard it with, say, like electromagnetic radiation, and it would say it would absorb the energy of that radiation and push the electrons out into the excited state. Good question. Just in general, oops, I'm sorry. Okay. So in general, when we talk about, I don't know, I wanted to go to this one. So when we talk about the excited state, it's simply a concept. You wouldn't, if you're asked to draw the Bohr model, it's assumed to draw it in the ground state. So you wouldn't, like, say, draw the Bohr model of hydrogen in the excited state. Always draw it in the ground state, unless otherwise specified. But a very concise answer as to what causes the electrons to jump levels: energy, added energy to the atoms. Okay, so I believe I left off talking about the differences between electron affinity and electronegativity, and they simply vary in name only. So electron affinity is the amount of energy released when we're adding an electron, and electronegativity is just describing the attraction of electrons. So although they vary the same way, they mean two different things. So fluorine has both a high electronegativity. A very high electronegativity, and it also has a very low electron affinity. So meaning that it's not releasing a ton of energy when we add an electron to it, but it's also it's attracting electrons to it a lot. So those two sort of go hand in hand, and their trend is the same, sort of going this way. Alright, so we can talk about ionization energy now. If you have any more questions on any of this stuff or anything else, be sure to ask away. But ionization energy, and this is basically the opposite of electron affinity. So electron affinity, we're adding electrons to our atom. For the ionization energy, we're simply taking electrons away. So we're removing an electron completely. Explain the ionization energy exceptions. Okay. So are you talking about exceptions to the trend of ionization energy, which is sort of as we go up this way, our ionization energy increases? So are you asking for, like, exceptions to that trend? Okay. In terms of that, obviously we have the noble gases on the right. So here are our noble gases, and as we go right, we're sort of getting a higher and higher. I'm sorry, no, these are included. So forget that about fluorine. Ionization energy. As you go up and to the right, our ionization energy is increasing. And again, I can sort of talk about why that is. And this will be important to understanding our exceptions. So francium, its outer electron, it only has one, so it only needs to lose one to achieve its octet. So number of valence electrons, a factor. This electron is very far from the nucleus and experiences a lot of shielding. So, that's certainly things to consider. And so, as we sort of do this, that's changing until we get to helium, which has a full octet, so it doesn't want to lose any. And its electrons are also very, very close to the nucleus. Now, if we look at our electron configurations for, let's say, beryllium and boron. So for beryllium, I won't be lazy, I'll write out the full thing. 1s2, 2s2. Boron is 1s2, 2s2, and then 2p1. And so when we do this, we actually find that boron here has a lower ionization energy. And that would sort of seem surprising, considering that, okay, so why it's less for O than N. Yeah, so I'll talk about that. So for here, it's sort of obvious why, or now that I write out the electron configurations, it's sort of obvious why I have a lower ionization energy. You would expect, as I go right, our ionization energy should go up. But here it's actually going down as I do this. And that's for a very good reason, is that our electron configuration here has this sort of 2p1, and that's going to be easier to remove than our 2s2. And so it turns out that this 2s2 electron is just a little more stable than our 2p1. And so I think you commented a very good question. So if we look at I keep saying electron affinity, ionization energy, and energy for N is greater than oxygen. And so this seems, sort of paradoxical to the general trend of, as us going right, electron affinity ionization energy goes up. So here we're moving right, our ionization energy is going down. So what happened? So again, let me look at our electron configurations. For oxygen, 1s2, 2s2, 2p4. For N, we have 1s2, 2s2, 2p3. Okay. So the electron configuration of nitrogen is sort of a stable, sort of half-filled structure. That being said, oxygen is one electron beyond being stable. So when we take an electron away from this nitrogen, it's becoming less and less stable. However, when I take away an electron from oxygen, I'm removing the 2p4 electron, so that's making it more stable. So therefore, it's easier to steal an electron from the oxygen atom because it creates stability, whereas if you're removing an electron from nitrogen, it's becoming less stable. So this trend, you asked about, specifically about nitrogen and oxygen, and here we're talking about, and I just talked about beryllium and boron. So is it because the probabilistic distance of a p subshell is farther from the nucleus than the s subshell regarding boron and beryllium? Yes, that's absolutely why. And so here we can say that our exceptions are sort of here and here. That's where the exceptions come into play. So in terms of our ionization energy for, say, these versus these, when we were, I'm sorry, that's wrong, these versus these, as we remove electrons from here, our element is becoming more stable, whilst here it is becoming less stable. So therefore, it's easier to remove an electron from, say, oxygen and make it more stable as opposed to nitrogen. So I hope that sort of answered your question about ionization energy. And then again, talking about definitions, first ionization energy is always referring to removing the first electron, and then you can have second and third and so on and so forth. But as you go down group 5, the difference between ionization energies decrease. Okay, so you're saying okay, so what you're trying to say is that the differences between, say, like these two here is less than these two, and you're asking if that's because of the distance offsetting sort of the stabilization argument. Yes, that is why. As you go down, we have more shielding, and our electrons are farther from the nucleus. So that's why it sort of offsets it. Now these outer electrons are not being held as firmly by the atom. Again, if you have any more questions about ionization energy, do let me know. Otherwise, I can move on to, some other topic or whatever questions you might have about this stuff. I'd be happy to help you out on that. Why does the periodic table have weird numbers for atomic masses? Shouldn't they all be whole numbers? Good question. I talked about this in, I believe it was the periodic table video, but it might have been the atom. And Arnold's completely right. It's because of isotopes. An isotope is simply just the same atom but having a different number of protons. So think about, like, let's say, I'll scroll up to give myself some room. Carbon 12 versus carbon 14. So here we have the same number of protons because they're both carbon, but in terms of neutrons, here I have 6 and here I have 8. Okay, so that's simply what an isotope is. It just has a different number of neutrons, but it's the same element. And so the masses on the periodic table, if we look here, you're right. Carbon is 12.011. And what that basically is an average of the atomic masses of naturally found carbon. So we go out, we find a bunch of carbon. Some of it is carbon-12, some is carbon-14. Maybe there's sort of other carbon isotopes. And what we do is this. So we'll say atomic. So we're just simply taking the sum of the atomic mass times percent occurrence. And then just summing that all up. And that's basically giving us an average of what the average atomic mass is. So that's what it is. Alright. Okay. Good. And no problem. Glad that you are no longer confused. Okay, so any other questions? Again, you can just simply ask away, but otherwise I can move on to some other stuff. Alright, so I believe we've covered this. Okay. Alright. So, in our previous videos, I'm sorry, the videos this week, would it be atomic mass times percent of occurrence of mass isotope times percent occurrence? Okay, so would it be... Okay, I must have written down atomic mass, but... Okay, and again, I'm on the wrong video. Okay, so I wrote down atomic mass. This should be isotope mass. Thanks for catching that. So yeah, because it's just the mass of the isotope you're dealing with. But yes, you're absolutely right. So isotope mass times percent occurrence, all summed up, will give us our average atomic mass, and that's these numbers here, and that's why they're sort of weird. Okay. So in this week's videos, we talked about the periodic table, and we also talked about factor labeling and sig figs. If you guys had any questions about that, maybe practice solution or something, be sure to leave a question. Otherwise, I can just sort of move on to some other stuff. I find that always sort of understanding what these, if I go back to my periodic table, alright, so now I can go here. Okay. So I always find that sort of looking down the groups and looking at the properties of these elements, and if I can understand why those properties are the way they are, I know that I've definitely grasped sort of topics that I've talked about in these videos. So these are called the alkali earth metals here. I'm sorry, alkali metals, not alkali earth metals. So these are the alkali metals, and they're very reactive. Can you list common things we need to memorize for factor labeling? Like what units? Okay. So I sort of talked about this in the last live stream, and this video is coming out on Monday, so you'll have that. But here is a giant table of the metric conversion factors. So you should definitely be aware of these. And you have to know several things. Well, first, is you have to know the prefix and the symbol. So sometimes you might say, oh no, you're fine, I'll just talk about this. So, okay, yeah, sounds good. Yeah, I guess I'll just talk about this. Or you can see the video tomorrow, and then if you have any questions next week's live stream, feel free to ask. You could also leave a comment on the video and I would respond. Anyway, I believe I was talking about sort of looking at properties on the periodic table. Okay, yeah, good deal. So if I'm looking at the periodic table as I was talking about, our alkali metals are, I said, are very reactive. I'm sure there's a better word for that, but I'm just struggling to think of it right now. Yeah, I don't know. Okay. But we're trying to think about sort of why that is, and then I can talk about it for other groups as well. So if you think about it, the chemical properties of an element is defined by its electrons. And more specifically, it's defined by its valence electrons. So as I talked about early in the live stream, we have the Octet Rule. Every element wants to have a full outer shell. So if we look at these alkali earth metals, I said they're very reactive. That's because these all have one valence electron. So they're really close to having a full outer shell. So they'll sort of give an electron to any element that wants one, like say, oxygen typically wants 2 to fill its octet. So lithium is more than happy to just give one away to oxygen. However, if we had like scandium here, has 3 electrons, and if it tried to give 3 to oxygen, oxygen, wouldn't take it. It only wants 2. And so that sort of explains this, is that these are very reactive because they only have one valence electron, and they're sort of willing to give that away. And all these other elements here, with the exception of the noble gases, are more than willing to take it and fill their octet as well. Similarly, fluorine, chlorine, bromine, iodine, astenine. These are all very reactive as well because these have 7 valence electrons, and all they need is one more electron to fill their octet. And so sort of any atom that's willing to give them electrons, they're willing to take it. So again, if I use the example, if I had scandium is willing to give away 3 to fill its octet, fluorine will gladly take it. However, carbon needs, fluorine will gladly take 1 of those electrons, and it'll sort of bond with anything. And so that's why these two are all very reactive. So I guess that's just sort of understanding concepts. Again, right now we're just sort of getting into it, trying to understand concepts. So that's why I'm going over this stuff. As we go along the year and we do more in the videos, I can do more calculations, or I can continue doing this. It's really sort of up to you guys. But if we don't have any more questions, I can move on. And so, in the spirit of plugging stuff in and... Okay, yeah, I was just about to give you one. So, we have, let's say we have 2 isotopes Okay, I'll write out the AP question because I guess that's like more professional or whatever. Okay, so silver has 2 naturally occurring isotopes. AG 107. Okay, I'll make this a little more clear. AG 107 okay, RIP, has an atomic mass 106.91 AMU and accounts for 51.82% of silver atoms. If the atomic mass of silver is 107.87, what is the mass of an atom of the second silver isotope? So here I'm sort of assuming that we only have 2 isotopes. So sort of as we talked about earlier, our atomic mass is just an average of naturally occurring elements. And so here we can say that our average mass is 107.87, and that's AMU. I didn't specify it, but it's probably safe to just assume that's AMU. And then we have 2 isotopes. So our first has a mass of 106.91 AMU and occurs 51.82% of the time. Now our other one has a mass of we don't know and occurs, let me just quick get my calculator out here. I just want to make sure that I don't mess up the subtraction here. Plus, I'll need it later. And occurs 48.18% of the time. Alright, so this is a good place to start. And so now we just need to determine how many AMU the mass of the second isotope is. So that's what the question is asking. Alright, so we know that 107.87 is equal to 106.91 times the percent occurrence. Okay, so you've got the answer. You're one step ahead of me. I'm sorry, this is not that. 0.5182, because that's percent. 0.4818x. I'll just sort of try to fly through this because I think you've already got an answer. So if I simplify this, simply just doing some basic addition and subtraction. I'm going to get on the left-hand side 52.469, and then here equals 0.4818x. We divide both sides by 4818, and I get 108 point. Okay, so your answer is actually incorrect. So, and the reason's twofold. First, we got to this same number here. I don't know, maybe that wasn't your answer. But you have to divide by 0.4818. Okay, and secondly, so what we're going to get, if you're confused, is 108.90. And this is because, look at our sig figs here, and here we both have 5, so it's important that we have 5. And secondly is that we want the atomic mass. We're not looking for, say, the molar mass, which would be grams. Here we want the atomic mass, so this is going to be in AMU or in Daltons, which are both the same thing. Yeah, I'm guilty of it too. No worries. So that's how you would do that problem. We're in sort of the last 10 minutes of the live stream, so if you have any more questions, sure to ask away. We don't have much time left, but certainly enough time for 1 or 2 more problems. Okay, so I want to think about a different conceptual question. Most atoms on the periodic table exist mainly in the blank state. So I'm basically asking, out of all of the atoms on the periodic table, naturally occurring, most are either liquids, solids, or gases. So take a second to think about this one, and I'll sort of explain it. Alright, so if we think about the periodic table, I'll just draw like a blank, terrible periodic table. I know that, okay, so your guess is gas. Okay, so all over here, these are all metals. Except, and then we have hydrogen, which is a gas. Okay. So, all these on the left are metals. These are the alkali metals and the alkaline earth metals. Here are the transition metals. Over here we have a bunch of different things. We have, like, here are the noble gases. We also have, like, the halogens and other sorts of stuff. And then, if you really want to get picky, we can also put in the lanthanides and halcyonides below. Sort of like so. Okay, so sort of as like a visual representation, I'll fill in the ones as they exist as I erase the entire thing. Okay. So here if we have, so I'll highlight in blue what the gases would be. And then I'll highlight in yellow the liquids. I mean, this is just sort of a guess. I don't actually know where they exist. But, and I won't do that because I don't know. But all of these here, these are all solids, mostly. You know, there's exceptions like mercury and stuff. And so, if I go to the actual periodic table, we can see this. All of these are all solids. These all exist as solids. So the answer here is solid. And that's just because of the sheer number of transition metals, alkali metals, alkali earth metals, lanthanides, actinides, and then as well as some of these down here are also solid, like, or no, I'm sorry, iodine. Iodine is no, iodine is a solid. Yeah, so these are all solids as well. So yeah, the answer is solid. I don't know, did that confuse you? Did you? Okay, so yeah, I mean, so the answer here is mainly in the solid state. So if that confused you at all, just be sure to, leave a comment. I'll try to do my best to answer in the time we have left. Maybe he was talking about oxygen. Okay. Yeah, I don't know. But definitely the answer to this one is solid. Anyway, we are reaching like the last minute or two of the live stream, so if you have a question, if you have any other remaining questions, just ask away. I'll sort of wait to see if we have any more. Alright, so it doesn't look like, do you know any good online resource that has good AP Chem multiple choice questions? Okay, so that's a good question. The first thing, obviously, go to our website, go to the resources tab. That's going to give you some good stuff. Online, probably Khan Academy has some stuff on their website. Other than that, I would just Google AP Chem multiple choice questions. We have a bunch of practice AP test links in this resources tab, but for right now, those might sort of confuse you. They might ask about things that you don't know, but you could certainly go to those practice AP questions and just sort of do the ones that you've covered. So that's certainly an option. Otherwise, if you still think that you're not getting enough resources, enough practice multiple choice questions, check out our resource recommendation video, or you can also look at the article in the resources tab where we talk about books that, some might have not very many multiple choice questions, some might have a lot. And so you can certainly check out that video and we'll sort of talk to you about, which book is best for you if you find online resources lacking. Mr. Milanic would be my last name. But thank you. You have a good week as well. Good luck with all your AP Chemistry studying. If you like the live stream, like the video. We've got our live streams coming back next week, so I'll see you guys then. Thanks for watching.